Well, for our final project for electromagnetism, we built a wireless charger, and our team is Takeshi Nakauma, Carlo Crivelli, Iker Bali, Victor Godinez, and me, Edgar Pérez. Well, first we need an introduction to this project, and we need to see the diagrams in the right side of the diapositive, and then introduce what will consist this wireless charger. And this wireless charger is composed by two parts principally, the transmitter and the receiver. The transmitter works receiving a DC current and turning this one to a AC current, which is transmitted by a coil built with with magnetic wire, and then connected to the second circuit built, that is the receiver, connected by both coils, and this receiver will charge the phone, receiving the AC current from the transmitter and turning this one again to a DC current, but now this DC current will charge the smartphone present in that circuit. For this experiment, we will need the following materials: two protoboards, magnetic copper wire, LEDs, insulation tape, MOSFET IRFC44N, resistors of different values, one multimeter, 5 diodes, model 1N4001, an oscilloscope, one current source, two expandable USB cables, some ceramic capacitors of different values, an electrolytic capacitor of 100 mu F and one electrolytic capacitor of 10 mu F, two heat skins for transistors, one MOSFET model L7805CV, and finally a cell phone charger.
For better understanding for this project, we analyzed in the class different types of circuits. The first one, it's this circuit, the RC circuit, where we have a source of energy, a current, and a resistance, and in which we can know its equations that are in the bottom of this slide. And we can know that in this circuit, the electric energy stored in the capacitor dissipates in thermal energy through the resistor. The next circuit that we analyzed in class was the RL circuit, that in which we know that the magnetic energy stored in the inductor dissipates in thermal energy through the resistors, and the equation of the circuits are in there. The third one was the LC circuit, in which we can see how it changes from the last one, making it a little bit more complicated. All the electric energy stored in the capacitor goes into magnetic energy stored in the inductor and vice versa. So the energy is conserved, and the equations for this circuit are in the bottom. And lastly, the RLC circuit is the last type that we saw during the class. And this is the most important type of circuit for this challenge, where we have the next equations and we can see its scheme on the right. And this is the most important circuit because it is similar to the one that we use during this challenge.
So, well, now we're going to talk about theoretical application. Like we mentioned before, this is an RLC circuit. It stands for resistant, inductor, and capacitor. Due to the Kirchhoff's laws, we know that sum of these three has to be equal to the voltage produced. So all of these three can be expressed in terms of the charge between the time. So we can obtain a second differential equation from here. So the only thing that we need to do is put everything in terms of the charge. And for example, in L, we can see that it's in terms of the change of intensity, but intensity is the change of charge in time. So we can see that it really can be seen as the change of charge in time. I mean, the second derivative. So we can see that at the end we get a differential equation where we can see that it involves the inductors, the capacitors, the charge, and the time, and the voltage produced. After that, due to the fact it's an operation that may be too hard to do analytically, we proceed to use MATLAB. In this case, thanks to Professor Victor Robledo, we were proportionated with a code in MATLAB that help us to see how does this circuit works. And we can see that here are some initial conditions that, well, that type of condition can change. It depends in every type of model, but in this case, we are considering these conditions. And well, we put our equation that we do before. This type of data has to be known in order to solve this differential equation. So, well, we here obtain all the data necessary in order to graph the three types of cases we have with respect of time. That would be charge, would be a current, and would be the change of charge.
Well, then after doing that part of MATLAB, we decided to do the graphs. In total, we have 3 graphs. The first one is the charge and the capacitor versus the time. The second one is the current and the resistance versus the time. And the third one is dy divided by dt versus time. As you can see on the first one, the Columbus one, we can see that the charge starts on 10, and then it starts bouncing from 10 to minus 7.5 approximately. And then while the time is passing, the charge is getting closer to 0. And almost at the second number 4, it's 0. And then from then to the second number 10, it's 0 always. Then the second graph, the Amperes one, which is the time versus the resistance current. At first, the resistance is 0, but when the current is applied, it goes down to minus 100, and then it goes up, and then the same as the graph before, it starts to get closer to 0 while the time is passing. And also by the second number 4, it's almost 0, and then from then to the second number 10 again, it's 0. And then the third graph, which is the Amperes one, the time versus the current of charge, which is one is dy divided by dt. This one started in minus 2000, and then again, at the same as the last graphs, while the time is passing, it is getting closer to 0, and by the second number 4 again, it's almost 0, and then from then to the next seconds, it's 0 again.
Well, now that we know about the theoretical information about a circuit and an ideal case and the behavior of an ideal case, we can talk about our prototype, our experiment. So for the first session of laboratory, we made the transmitter by following the diagram given by the teacher, when we had to connect those wires that you can see in the protoboard. And we had also had to build 2 coils, smaller than the big coil, to prove the functionality of the circuit. And to prove this functionality, we need to connect our protoboard to directly to a current source. And if the LED on the protoboard turned on, the first part is okay. But the second part, you need to put that small coil inside the big coil, and if the LED turn on, it is also correct. But in our case, when we connected the transmitter to the current source, the LED on the protoboard turned on, so that part was okay. But when we put our small coil inside the big coil, the LED didn't turn on. So there are a lot of reasons, like maybe one part of the circuit was wrong, so it makes the whole circuit fail. Another can be the small coils like the labs or the form, because that determine the electric conductivity. But in our case, the factor that made the circuit of the transmitter failed was the capacitor, because it was burned and it made the current received by the transmitter couldn't be converted into an alternate current. This was proved using an oscilloscope. And if our transmitter was working correctly, the oscilloscope had to show a graphic with a geometry similar to a sine function. But when we try to show the electric current of our transmitter, the oscilloscope has showed a very amorphous graphic. So that means that one of the components was burned. Now for the receiver, we built it in the second laboratory session. Like the transmitter, we followed a diagram given by the teacher, and we need to build another coil and connect the wires, as you can see on the protoboard. And now that now that we have both transmitter and receiver, we can join them and have our final prototype.
Well, after following the both diagrams and the instructions given in the class, we built our final prototype, and this one looks like that. But we have to mention that we have a problem with our transmitter, because the transmitter, it doesn't make the work correctly. This because one of the most important components failed, and this one is the MOSFET that we needed to build the transistor. This component didn't work because it got burned, because in one of our tests before putting the coil with the LED in the another coil connected to the protoboard. And we have to mention also that we had built the receiver just to complete the both circuits and made our prototype look like that. But if the transmitter doesn't work, the receiver obviously doesn't work too. And finally, we can conclude that in this course we've learned that how works some different kind of circuits and with different currents, like AC and DC currents, alternate currents and direct currents, how a circuit can turn an AC current to a DC current and vice versa. And then we also have to mention that we learned too that in the laboratory we need to take care of our materials, because if one of those doesn't work correctly, can bring down all our project and the circuit will not work correctly. And we also need to take care of another components that we had built, like the coils, that if the number of turns increases, the electric current in the coil will increase too. And that is mentioned just to give an example of taking care of other materials. And then finally, we can say that this project will going to be is important to this class, and probably we need to use the most of these concepts in the future of our careers. And that's everything. Thanks.